My name is Tae Kim, and I will be going over Lab 4 circuits and capacitors today. So the purpose of the lab is to predict the behavior of circuits containing resistors in both a series circuit and a parallel circuit. And we use multimeters to measure the actual values for the current and the potential differences in the current circuits. And we examine the behavior of resistors and capacitors in the circuits. And the procedure for this lab was basically using the CCK to simulate a circuit in an ideal situation utilizing multimeters, resistors, and capacitors. Some of the key concepts is the conservation of energy, or the loop rule, which states that the sum of the potential difference in a complete loop has to be zero. Similarly, the conservation of current, which is the node rule, states that the current entering an intersection is equal to the current leaving that intersection within the circuit, sorry. And then finally, we use the Ohm's law, which states that the potential difference is equal to the current times the resistance. So in the first diagram shown on the right, I predicted that the current would be 0.0204 amps using the calculations that I've showed. And the actual current was found to be 0.02 amps, which is very close to my prediction. And I1 and I2, which is each of the currents at ammeter 1 and ammeter 2, shown in the diagram on the right, they are equal because there are no split junctions. And when I reverse one of the ammeters, the current was found to be the same but negative, so negative 0.02 amps. And in the second diagram, where I replaced one of the ammeters with a voltmeter, the potential difference was found to be 3 volts. And the current is zero because the circuit isn't closed. It is an open circuit, so there is no current. Okay, this is an overview of my results. As you can see, I have labeled all of the corresponding potential differences from each point on this diagram, and I've also showed it on this table. And this satisfies the conservation of energy, which is the loop rule, which states that the sum of the potential differences is equal to zero, which is our case here. And just looking at this diagram, it shows the voltage across different points, and that just summarizes the results found in the previous lab. And the voltmeter has an infinite resistance, which means that does not change the value of the ammeter. So that's why in this part, it does not change the value of the ammeter. And then when I changed our circuit to a parallel circuit, the current was found to be 0.06 amps, which is greater than the 0.02 that was found from before. And this is because the current has increased because the ammeter has a low resistance, so it makes it easier to flow through the circuit. And these are just the resistance values that I found for each of the circuit elements. Um, and the 47 and the 100 resistor both are pretty similar to 47. So 47 resistor is very close in 47.95 ohms. And the 100 resistor has a resistance that is very close to 100, which is 102.05 ohms. And in our simulation, which is an ideal setting, the wire and the ammeter both have zero resistance. So in our RC circuit, we have simulated the charging and the discharging of a capacitor. So when the capacitor is charging, which is shown on the top diagram, the light is bright and then it gets dimmer as time passes on, and the current decreases as time passes on as well. And it took around 8 seconds to charge the capacitor with a 10 ohms light bulb, and it took 20 seconds to charge the capacitor with a 20 ohms light bulb. Similarly, for capacitor discharging, the light is initially bright and it gets dimmer, but it is brighter for a longer time than it is in the charging capacitor. The current is also decreasing as time passes by. It took 10 seconds to discharge the capacitor with a 10 ohms light bulb and 20 seconds to discharge the capacitor with a 20 ohms light bulb. Finally, the last procedure was to measure the potential difference as time was passing in a discharging capacitor. And then I graphed the ln of the potential difference over the initial potential difference over time. And as you can see, it's a linear relationship. It is going down as time is passing by. And the slope of this graph is found to be negative 0.1527, which is actually negative 1 over RC. So the RC value was found to be 6.548, which is pretty close to the predicted of 6. And some of the reflection questions, the first one is, what if we were doing this lab in real life? And how would that be different using a real simulator versus an ideal? And since the ammeter has a small resistance that is not zero, it'll decrease the value of the current. And similarly, what if you were doing this lab in a real life and used a real battery to charge a real capacitor with no resistor in the circuit? And how quickly would our ideal model predict the capacitor to a full charge. So the ideal model does not count for resistance, so the capacitor was charging instantaneously. However, if we simulated this model in a real scenario, it will take longer than the ideal model because the batteries and the wires have a small resistance in real life that are not zero. Thank you for listening.